welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are discussing the paper called data structures, and in this particular module we will be talking about 2, 3, 4 trees. As you have already seen in the previous modules, we have spoken about binary trees, binary search trees, and then we went into balanced binary search trees, where we saw two types of balanced binary search trees, in fact 3. One was called AVL trees, then we saw red black trees, and then we saw splay, which was a self adjusting type of binary search tree. Then interestingly we went to multi-way search trees, where in the last we had spoken about 2, 3 trees. Now we are going to a little bit more of a multi-way, in the sense that we are going for 2, 3, 4 trees. So, let us start with the learning objectives. First is to understand the concept of 2, 3, 4 trees, then to discuss insertion into 2, 3, 4 trees. Here it is a little bit interesting of how this is done, how the splitting is done. In the previous module we did splitting for 2, 3 trees, here we are talking about splitting of 2, 3, 4 trees needed for insertion into these 2, 3, 4 trees. To describe deletion from 2, 3, 4 trees, and to discuss some of the advantages and also some of the disadvantages of 2, 3, 4 trees. So, keywords are again multi-way trees and redistribute and merge. Remember, we looked at redistribute and merge in a when we were discussing 2, 3 trees. We are going to look a little more detail into that when we are talking about 2, 3, 4 trees. Now, let us discuss first, let us see what are 2, 3, 4 trees. So, 2, 3 and 4 in the name refer to how many links to child nodes can potentially be contained in a given node. So, in a given node you can have either 2 children, I mean corresponding to a node you can either have 2 children, or you can have 3 children, or you can have 4 children. That is why it is called 2, 3, 4 trees. For non-leaf nodes, 3 arrangements are possible, as I already discussed. A node with only one data item always has 2 children. So, again as before in 2, 3 trees, the data item is 1 less than the number of children a node has internally. So, in a node with only one data item you can have maximum of 2 children. A node with 2 data items can have always has 3 children, not maximum, always has 3 children. A node with 3 data items always has 4 children. So, a node with 1 data item 2 children, 2 data item 3 children, 3 data item 4 children. For non-leaf nodes with at least 1 data item, a node will not exist with 0 data items. The number of links may be 2, 3 or 4, that is what we basically are talking about. That is for non-leaf nodes, which we saw before, there must be at least 1 data item. If that 1 data item is not there, the node does not exist, and the number of children obviously can be only 2, 3 or 4 depending on the number of data items that you have. Equivalently, if the number of child is L, the number of data items is D, and L is equal to D plus 1, that is the number of children will be 1 more than the number of data items. So, the number of data items will be 1 less than the number of children. Okay. Now, this is an example of a 2, 3, 4 tree. It has an example of it is a lozenge shaped, and in a 2, 3, 4 all the leaf nodes, just like in 2, 3 trees, all the leaf nodes are at the same level, the leaf, and data can appear in all the nodes just like there, but the all the leaf nodes will be at the same level. So, this is an example of a 2, 3 node that we 2, 3, 4 node. If you look, then the root node has 2 children, the left subtree of the root node has 2 children, the right subtree of the root node has the maximum 4 children, and so on. And the number of data items in the leaves, all the leaves are at the same level, can be 1, 2 or 3 maximum, okay, data values. Now, rules for placing data items into the nodes of a 2, 3, 4 tree. What are the rules? 2 children must contain a single data item that satisfy the relationships. What are the relationships? We will see the relationship. 3 children, if you have, it must contain 2 items, data items, and must satisfy the relationship. If you have 4 node, 3 node and 4 nodes, 4 child nodes, then it must contain 3 data items and it must satisfy the relationships. Because a 2, 3, 4 tree can have nodes up to 4 children, it is called a multi-way tree of order 4. So, in the binary search tree is called a multi-way of order 2, or binary multi-way of 2, 3 tree is called multi-way tree of order 3. Maximum number of children it can have is 3, and 2 3 4 tree is a multivariate tree of order 4. 2 3 4 has trees have some very nice features. Now, let us look at these features. Are always balanced. Now, what is the meaning of balance? We have seen what is the meaning of balance, but in this context what does it mean? Reasonably easy to program, serve as an introduction to the understanding of B trees, which is very important. B trees is a very important data structure as far as database is concerned, for storing keys of database is concerned, and this is a very good introduction to that. From the 4 way we go to an M way, that is the B tree. So, it is very good for understanding B trees, and B tree is another kind of multivariate tree, particularly useful in organizing external storage like files, as I already told you. And it can have dozens or hundreds of children with hundreds or thousands of records. So, this is why B trees is very important, and we will go to understand the concept behind B tree. If you understand 2 3 4, it is just an extension. Okay. Now, just look at this. Let us talk about a node in a 2 3 4 tree. It will contain 3 data values S, M and L, let us assume. Now, what is the we said it has to satisfy some conditions or properties. So, if you have a 4 node, the 4 node is the node with 4 children and 3 data values S, M, L, then the condition is S is greater than the left items in the left child item. So, we will call this having 4 middle left child, middle right child and the right. So, left, middle left child, middle right child and the right. So, if you do that, S is greater than the left child item and greater than that and lesser than the middle left child. M is greater than middle left child and less than middle right child, and L is greater than middle right child and less than right child's item. So, just let me repeat, it is to say if you have S, all the items to the left tree will be less than S, middle will be between S and M, middle right will be between S, M and L, and right will be greater than L. That is easier to understand. Data items less than S on the left, data item between S and M in the middle left child, between M and L in the right middle right child, and greater than L in the right child. So, these are the 4 things, or in other words, that is about the trees. S will be greater than the data items in the left and less than what is in the middle left, and so on. So, this is the 2 3 4 tree, the property of a 4 node. A leaf may contain either 1, 2 or 3 data items. Okay. So, this we have already just discussing it once more with to re-emphasize the fact, in a 2 3 4 tree there are 3 types of nodes: a 2 node, a 3 node and a 4 node. A 2 node has 1 value and 2 maximum of 2 children, 3 node has 2 values and 3 children, 4 node has 3 values and 4 children. The numbers refer to the maximum number of branches that can leave the node. Now, if you take the 2 node, so it has only 1 value. So, it is same as a binary tree node. So, the value at the left is less than A and the value on the right is greater than A, where A is the root. Now, you take the 3 node, 3 node has 2 values, okay, and 3 children. So, A and B let it be the value, and the condition is A is less than B. So, the value to the left is lesser than A, value in the middle is between A and B. So, it is lesser than greater than A and lesser than B, and value to the right is greater than B. So, that is the 3 node. The 4 node, this is the same as the 2 3 node, no other thing. Now, 4 node has 3 values A, B, C, such that A is less than B is less than C, and so now we will call this as 4 children. The 4 children, let us call it as left, middle right and right. So, the left child has value less than A, the middle left child has value less than A, I mean greater than A but less than B, middle right child has value greater than B but less than C, and left child has value greater than C. This is all that we are talking. This is the search property as far as 2 3 4 tree is concerned. It is a search property. We are not talking about anything about that other than the search property. The search property is defined this way. Now, there are some properties of 2 3 4 trees. One is it maintains height balance in all the subtrees. So, that it has the depth property, but allow nodes in the tree to expand to accommodate inserts. So, it allows nodes to expand. So, if it had a one child node, one child, two child, two node, it can become a 3 node, a 3 node can become a 4 node. So, this is allowed. In particular, nodes can have 2, 3, 4 children. So, it is called a node size property. So, it has a depth property, it has a node size property, and 4 node would have 3 keys and split the keys into 4 intervals. Okay. Right. Searching and traversing in a 2, 3, 4 tree. Let us discuss that. Simple expansion to the corresponding algorithms for 2, 3 tree. We will see how it is expanded. Inserting data into a 2, 3, 4 tree. Insertion algorithm splits a node by moving one of the items up to its parent's node. So, that is what we did in 2, 3 tree, but here there is a little more conditions which we have to satisfy. Splits 4 nodes as soon as it encounters them on the way down from the tree, from the root to the leaf. So, searching in a 2, 3, 4 to find an item, start at the root and compare the item with all the values in the node. Now, if there is no match, move down to the appropriate subtree. Repeat until you find a match or reach an empty subtree. So, till you do that, you keep finding. So, you start there, and then which direction to move is told by where the value comes. Okay. So, insertion, find the place for the item in the usual way that you do. On the way down the tree, if you see any 4 nodes, split them and pass the middle value up. If a leaf is a 2 or 3 node, add that item to the leaf. If the leaf is a 4 node, split it into 2 nodes, passing the middle value up to the parent node, and then insert that middle value to the parent node. If that is a 4 node, again you have to split, similar to what we did in a 2, 3 tree. There will be room because 4 nodes were split on the way down. So, that condition, that repeated splitting is not necessary, we will see. Now, splitting nodes during insertion. So, the first case is now suppose I have SML and having 4 subtrees values A, B, C, D, that is called the subtrees as A, B, C, D. How do you split this? So, splitting a 4 node root during insertion, let us assume it is a root during insertion. What will you do? You will split it such that you have a parent and the A and B is put as a child with AB as its children and L as CD. You will notice that the search property is still maintained. So, what you are doing is you are splitting it. Okay. Now, let us look at the splitting a 4 node whose parent, now here we are splitting it in such a way that you are splitting a 4 node whose parent is a 2 node rather than a 1 node, it is a 2 node. So, here we have a 4 node SML whose parent is a 2 node because it has a value P and it has a child E. So, you are trying to split SML. When you split SML, what happens? SNL are split as before, M moves up. Okay. So, M moves up and now that parent node will have 2 values, it becomes a 3 node. So, from a 4 node connected to a 2 node parent, now you are splitting it and making the 4 node be connected to a splitting it, moving one value up and making it into from a 2 node into a 3 node. Now, on the third side, so splitting a 4 node whose parent is a node 2 node during insertion into a 2, 3, 4, where the 4 node is a left subtree. In the other case, in the next case, we had the third case, we have where the 4 node is a right subtree. So, if it is a right subtree, the similar, but where you place the M and where the child comes, if you look at the 4 node in the ABCD E condition, the D, CD and E came. Here you have again CD, I mean BC and CD coming as before. So, you see here in the initial case M moves up, in the second case there was no parent, in the second case M moves up and is placed before P because you had a left child. Here you had as a right child. So, M is moved up, placed in the one child thing with M coming to the right of P. So, this is the basic splitting of nodes during insertion. Now, you have the next case, that was 3 cases. What was the 1 minute? Let us look at the 3 cases again. The first case was that it is a root. So, no parent. the initial node the root node has got 4 children, I am splitting it. When I split, what happens, I have in this case with no parent, what I have is 3 2 node instead of 1 4 node, I have 3 2 nodes, okay, 1 as parent and 2 as children. Now, the next case we had a 2 node, a parent with a 2 node. Remember, all the nodes are either 2, 3 or 4. So, it is a 2 node parent and a left subtree 4 node, and the 4 node being a left subtree. So, I split it up and it becomes a 3 and a 2 node. Similarly, in this, but here it is a right child. Now, we go to the next case, splitting a 4 node whose parent is a 2 node during the insertion, when 4 node is a left child. So, again you have a left child, right child. Here you have the 4 node being a left child, but here the difference is the parent already contains is a 2 node whose parent is a 3 node during insertion. So, here we have the parent now becoming a 4 node, becoming a 4 node with 3 values M, P, Q. Because it is a left child, it becomes a leftmost value. Now, the same case, only thing here it is a middle child, which one, the 4 node, because it is a 3 node the splitting of 4 node whose parent is a 3 node P and Q, and this M value that you have to place is going to come in between P and Q, because the 4 node is a middle child of the 3 node, okay, middle child. And the obvious case of the next one is it becoming a right child, it being a right child. So, here we have a 3 node parent who P and Q point to the A and B, the 2 children of P and Q, and the 4 node is the third child or the right child. So, now what happens when I split it up and you place it appropriately, the M goes, the middle value of that SML goes as the right the split goes to the right of the complete tree. So, if you look at all the 3 cases, the 4 node split goes and gets itself attached to the left when it is a left subtree of the original parent, middle when it is a middle of the original parent, and right when it is the right of the original parent. So, this is splitting nodes. We had 6 cases, 1 when it was the root, 1 when the and then 2 cases of when the parent was a 2 node, and 3 cases of when the parent is a 3 node. Okay. So, if it is a 4 node, you cannot, you have to do continuous split. Now, let us look at this insertion. So, insertion into 2 3 node, we are going to look at one case. So, first is you insert 60, just insert 60, then you insert 25, you insert 25, finished, you insert 100, you insert 100. So, up to now we have not violated any condition, we have 3 values in the leaf. Now, you insert 90, when you as soon as you see a 3 value node, to split a 4 node, move middle value up. So, this is a 4 node, it has 3 values, it is a 4 node. As soon as you see that 4 node, you are not waiting for the insertion to happen. As soon as you see, now it is not violated anything, it is a 3 value, but as soon as you see a 3 value 4 node, when you see that 4 node, you do a split. How do you do a split? To split a 4 node, you just move the middle value up. So, you move the middle value up, split 4 into a 2 node. Okay. So, this is what happens. Now, you insert 90. When you insert 90, what happens? No, it's you have 2 nodes and 1 3 node, nothing happens. So, you insert. Next, I want to insert 70. When I insert 70, what happens? I insert it, I get 70, 90, 100, fine, it is a 3 node, I mean it is a 3 value 4 node, I leave it as it is. Next, I insert 34. 34 does not cause any violation because it is going to the other side. So, I 2 node becomes a 3 node with 2 values. Now, I add 12. When I add 12, okay, we have 2 4 node children as the children of 60. Okay. Now, this is the scenario after I have added 12. Now, what I do is inserting 10 causes the node on the left to, the 12, 25, 34 node to split and 25 to join 60. So, what happens now? please note the previous node. I have 60, 12, 25, 34, 70, 90, 10 and the next insertion is 10. So, I have to insert 10 where in the 12, 25, 34. So, when I insert that violates the condition. So, I split it up and when I split it up I have 10, 12, 25, 34. So, I split 10, 12 into one side, 25 goes up and 34. So, that is what happens here. So, I get 25, 25 goes to the left of 40 and 34 comes here. So, now I have finished inserting 10 and there is no violation. I have at the leaves I have a 3 node, a 2 node and a 4 node. Now, I insert the next one which is 65. When I insert 65 there is when I insert 65 into 70, 90 it has to go to that right hand side. So, I get 65, 70, 90, 100. So, again there is a split 65, 70 comes 90 moves up. So, now and 100 goes to that side. So, now what happens none of the leaves I have 4 children a 3 node, a 2 node, a 3 node and a 2 node, but the parent is now a 4 node. So, this is what happens 4 node as a root. Okay. Now, next I have to insert now we have one 4 node as a root. Now, let us insert 88, 120 and 20. When I insert 88 no violation, when I insert 120 no violation, when I insert 20 again there is no violation. Now, I have lots of 4 nodes. I have root as 4 node, left as 4 node, then middle right as 4 node and the right as 4 node. So, I have lot of 4 nodes. So, now I want to insert 77. When I want to insert 77 it causes that node 65, 70, 88 to be split. When 65, 70, 88 is split, it is split as 65, 70 goes up and 77, 78 has been inserted. Now, what happens when I move it up, that node, that is when I move 70 up because of the insertion, I have 25, 60, 70, 90 which is again it has violated the condition. So, that again is split. So, I get 25, 60 on one side, 25 on one side, 60 goes up and 70, 90 comes this side. So, now I have this node where the parent has again been split. Okay. So, this is the insertion of 77. So, when we do insertion, as you can see we have seen two cases, one where the leaf is split and one level. Here we saw the leaf being split, the parent already being full and the parent again being split and a new node being created because of the insertion 77. So, this is the insertion into a 2, 3, 4 tree. As in the 2, 3 tree there is percolation of the splitting up the tree. Now, we go to deletion from a 2, 3 tree. First we have to find the value to be deleted and then we have to swap it with the in-order successor. This is similar to any search tree property. Binary search tree we just had in-order successor. Similar way we can define any search tree, we can define an in-order successor. So, on the way down the tree both for value and the successor upgrade 2 nodes into 3 nodes or 4 nodes. This ensures that the deleted value will be a 3 or a 4 node leaf. So, this is what we are trying to do. So, remove the value from the leaf. So, what we are trying to do is on the way down from the tree when we are searching both for value and successor you will be doing the search, upgrade 2 and 3 nodes into 2 into 3 or 4 nodes. When we do that, when we are doing a deleting, we will ensure that no violation of 3 or 4 occurs and then you remove the value from the leaf. So, let us see the procedure. Items are deleted at the leaf, swap them for an internal node with in-order successor. Note a 2 node leaf creates a problem because when you remove something it becomes a 1 node and there is no concept of a 1 node in a 2, 3, 4 tree. Strategy, different strategies are possible. On the way from the root down to the leaf, turn 2 nodes except the root into a 3 node. So, that there is no question of a 2 node and 1 node being deleted from that and becoming invalid. So, that is the upgrade cases. 2 node whose next sibling is a 2 node, combine sibling value and divide value from parent into a 4 node. By the algorithm parent cannot be a 2 node unless it is the root. In this case our new 4 node becomes a root, or so 2 node whose next sibling is a 2 node, or you can have a 2 node whose next sibling is a 3 node also. If that is the case, move this value up to the parent and move the divider value down, shift a value to the sibling. So, a little bit of rearrangement we do here. So, let us see these cases. First is turning a 2 node into a 3 node. Here there is a case 1 where the adjacent sibling has 2 or 3 items. So, steal an item from sibling by rotating items and moving subtree. So, again deletion of 2, 3, 4, there is a little bit of rotation. So, what do we do here? If you look here, what we have done here is we are this 10, 20 is being and you have 10, 20, 30, 50, 30, 40 and 25. Now, steal from sibling. So, you are stealing from 10, 20 roll sibling, you are stealing a node and placing it in the right sibling. So, you are moving it into a subtree. So, that is what you have done here. Case 2, each adjacent sibling has only one item. So, for example, here 10 and 40, the adjacent item has only one node. So, you cannot borrow from that because it is already in that danger case. So, what do? You steal from the parent and merge the node with the sibling. So, what you do? You steal from the parent. So, take 30 from the parent and merge 10, 30, 40. Node parent has at least 2 items unless it is a root. So, unless it is a root, it will minimum have, it will have 2 items. So, there is a merge operation. So, let us look at the efficiency of a 2, 3, 4 tree. So, in the deletion we saw that we do a merge and a rotate. So, it is guaranteed of the order of log n time for search and insert, very important. Searching for an item in a 2, 3, 4 tree with n elements, the maximum number of nodes visited during the search is of the order of log n plus 1. Inserting an element into a 2, 3, 4 requires splitting no more than log n plus 1 4 nodes and normally requires very far fewer splits. Okay. So, what are the drawbacks of a 2, 3, 4 tree? Awkward to maintain 3 types of nodes. You have 2 node, 3 node, 4 node and you have to say which is 2 node, which is 3 node, which is 4 node. So, that is an important issue because most of the operations both insertion and deletion require that I know what type of node I am dealing with. Need to modify the standard search on binary trees because you cannot do that. Split need to move links between nodes. So, links have to be moved, that is another disadvantage, and code has many cases to handle, lot of cases. Okay. So, that is some, and since any node may become a 4 node, then all nodes must have space for 3 value and it links. It is not that you can have 2 nodes have only less space, 3 nodes have less space, no, because when we are doing a operation, any of the node can become 4 nodes. So, all the nodes must be ready to be a 4 node. So, you should have place for 3 values and 4 links, okay, because any 4 node has to have 3 values and 4 links. But most cases, even though we maintain it like this, most cases are not 4 nodes, right. So, what happens? Lots of wasted memory unless implementation is fancy and you do some manipulations such that this is not needed. Complex nodes and links as we have already discussed, and slow load to process than a binary search tree, obviously, because we have different types of nodes to handle, that is the basic thing, and the links to manipulate. Okay. So, what have we done in this particular explain the concept of 2, 3, 4 trees, outline insertion into 2, 3, 4 trees. Now, this explanation of 2, 3, 4 trees is very, very important because this is going to be extended to B trees. So, B trees we will not go too much into detail, but you can see that just like we shifted the middle up, you could shift out of the M nodes, you could shift some nodes and split it accordingly, or you could merge it accordingly. So, that concept remains the same, whatever may be M. So, we saw 2 cases. In the last module we saw where M was 3, in this module we saw where M was 4. In B it could be B degree. So, there we have to look at it in a different way and describe deletion. So, in insertion we did split, while in deletion we did merge and redistribute, and we discussed the advantages and disadvantages of 2, 3, 4 Ds. So, in the next module we will be discussing about B trees, which is based basically on 2, 3, 4 trees. So, that we will do in the next module. Thank you.